we go over the collision model in chemical kinetics. Well, what is a collision model? What does it tell us about? Now, the collision model tells us that molecules must collide to react. So whenever there is a chemical reaction to happen, molecules must collide to react. This is basically about the collision model. And so this collision we are talking about is what is called collision frequency. Well, for a chemical reaction to happen, there should be a certain kind of collision between particles. So if the collision is not there, it is not possible to have a chemical reaction happening. Now, at the same time, it is found that it is not every kind of collision that produces a chemical reaction, because some kind of collisions have got improper molecular orientation. For example, if you are talking about an hydroxide, okay, let's say reacting with hydrogen. Now, how does this have to collide? You can have a lot of hydroxide and a lot of hydrogens colliding. We know now, in this case, we are talking about hydrogen ion, so it is positively charged. When it comes to an hydroxide, one of these is positively charged, one of them is negatively charged. Because they are different electronegativities, oxygen and hydrogen have got different electronegativities. And so, because oxygen is more electronegative than hydrogen, it tends to pull electrons toward itself, and so it gains a partial negative charge. And then the hydrogen gains a partial positive charge. And so there is a partial negative this side, there is a partial positive this side. For the collision to happen between an hydroxide and hydrogen, of course, this can be colliding and such a thing. But if this kind of collision happens, there will be no chemical reaction that is going to happen. Why? Because the orientation is not right. Okay. For a chemical reaction to produce, for a collision to produce a chemical reaction, the orientation should be in the right order. That means the negative charge should collide with a positive charge. And so the orientation is supposed to be, unless hydrogen ions collide in this direction with hydroxide, where this is partial positive and then partial negative, then a chemical reaction is going to happen in this case, not in this one. So for the first one, the orientation is wrong, though collisions can happen. For this one, the orientation is correct. And so one thing that we've seen is, for a chemical reaction to happen, one, there should be collision. How many collisions are happening? So the more the collisions, it's all about probability. The higher the probability, the higher we are talking just about chance, the more the chances of a reaction happening. So if there are more collisions, you have got high chance that a chemical reaction is going to happen, because when you have got a lot of collisions, there's high chance that there's going to be a lot of correct orientations. So the second thing is correct orientation for a chemical reaction to happen. Now, it doesn't just end on correct orientation. Remember, for a collision to happen, what is happening is these reactants have got kinetic energy. So they are able to move to and fro. So because they are able to move like that, they've got that kinetic energy. When they start colliding, the kinetic energy is being converted into potential energy, because collision makes some stop moving and such a thing. And so that kinetic energy is being converted into potential energy. And that energy which is converted to is going to be used now to break some bonds and to form some other bonds. So there is a time when bonds of the reactant, say you're talking of A reacting with B to produce C. There's a time when these bonds, okay, let me not say C, but let's say AB. Now, because we don't have any compound here, I might not explain. Well, let me use a compound where, okay, let's say we have got AB reacting with C to produce AC and B. So this is a chemical reaction that is happening. And so for this reaction to happen, these compounds have to collide. So that means if C is having a partial negative charge, B should have a partial negative charge also, and then A should have a partial positive charge. Why? As we can see, this one has a negative charge, this is also having a negative charge. That's why B has been removed, because it also has a negative charge. So C wants to get with this one which has got a positive charge. That's why AC is formed there. Now, for this to happen, when these compounds are colliding, we are saying collision, they've got kinetic energy. So because of that kinetic energy, as they are colliding, the more they continue to collide, the energy which is in form of kinetic is going to be converted into potential, and that is going to be used even to break bonds. So first, what is going to happen is this bond is going to be broken, and so there will be AB, just like that, a bond is broken. And then now we're going to have the C, which is now going to come and interact with A after the bond is broken. So you actually need a certain kind of minimum energy that has to break this bond which is here. And such energy is called activation energy. The minimum energy that has to be taken in for a chemical reaction to happen. So we have got what is called a activation energy barrier. So if we want to show on a diagram, we can show in that manner. So for this reaction, we have got the reactants at this point, AB, okay, AB reacting with C. So this is the energy at which they are. So on this point, we have got potential energy, because as they are colliding, kinetic energy is being converted into potential energy. So when they do collide, there should be a certain kind of energy that has to be overcome for this reaction to happen. Okay. And so this energy from this point to this point, this energy that has to be overcome, this is a barrier. This E we can see here is a barrier that we need to overcome for us to make sure that this reaction happens. Immediately we reach to the top, it will be very easy, because the reaction will just proceed like that. Think of it like this: it is not easy for you to move from down the hill to the top of the hill, but if this hill is slippery, for you to go down, you can simply slide down the hill, which is very simple. You don't even need any energy to slide. And so the job is for you to move from down the hill to top the hill. So such energy that you need for you to move from down this hill to up the hill there is what is called activation energy. The activation energy is the minimum energy that has to be supplied to overcome the activation energy barrier. So what we can see here is a barrier. Okay. Now on the top here, we are going to have what is called, on the maximum point, there is what is called a transitioning. So that is a transition state. So this is where now there is a change of state. These are going to break. They are now going to be into a form where they are broken. And so on the maximum point, you have got a mixture of reactants and products, a very point where the change of state has to happen. That is the maximum point there. Okay. And so what we are going to have is the bond between A and B has to separate on the maximum point there. And then now you have got even C just on top there. So at this point, this bond will be broken, and then on the minimum here, this is when you are going to have AC plus B. the product. So this is what happens. So this energy is very important. It is needed for the reaction to happen. And so that is the third thing that is needed for a chemical reaction to happen. Activation energy. Well, so the activation energy, so for this kind of reaction to happen is you need to supply energy to these reactants such that the energy that you supply is either greater than or equal to activation energy. Activation energy is actually the very minimum of energy that you can supply for a chemical reaction to happen. So if you supply any energy that is lower than the activation energy, a chemical reaction won't be able to happen unless you supply energy either equal to or greater than. Okay, so at the top there we have got what is called the activated complex. So this is what is referred to as the activated complex, or the transition state, where you have got the reactants which have broken into the bond between the reactants have broken, now ready to form product. For example, if you had the compound, let's say the reaction where a decomposition of this compound, alright, so this is the decomposition. So at the very start you only have this compound BRNO. Now at the maximum here, before it forms products, the bond has to be broken, and so on the maximum we're going to have what is called the activated complex, or the transition state, the point at which transition is happening. And so we're going to have the bond ON, because this is one compound here, and then bonded to BR. So because there is a 2 in front there, so let's put a 2 there, and this is going to be 2 times, so we can put a 2 in front there. So this is the bond that happens. And why is it that BR is on nitrogen, not on the part for oxygen that side? So we need to look at the charge. Because oxygen is more electronegative, it's going to carry a negative charge. This is going to carry a positive charge. So this compound wants to react with something that is positively charged because itself is negatively charged. That is why it's on the nitrogen instead of it being in this manner. That's why it is in the order that it is. That is correct orientation. So all this is needed. So at the maximum you have got the activated complex, and then after this activated complex is very simple now for you to form product, because all that is going to happen is these are going to break just and be able to rearrange into this. Okay, now one scientist joined all these 3 factors which are giving us a chemical reaction to start, and that is Arrhenius. And so Arrhenius brought up an equation called the Arrhenius equation, which tells us that for a chemical reaction to happen you need to have collisions which need to happen, and these collisions have to have correct orientation, and then there should be a minimum energy which is called the activation energy. And so the Arrhenius equation tells us that the rate constant for a reaction that is happening like this is given by A e to the power negative EA divided by RT. So this is the activation energy. Now all we need to get to understand is the values of what do these letters represent. So the A we can see here represents what is called a frequency factor. And then this is simply the Euler's number. It is it's about 2 point something. That's Euler's number. Okay, that is 2.718. 2.718. So this is Euler's number. You can just simply punch it on the calculator, it is there. And then now we have got EA, which is the activation energy, and then R is the universal gas constant, and then temperature, T is the temperature in Kelvin. Now, what does the frequency factor mean? Of course, we know what activation energy is. We know the universal gas constant. We know it. Simply a constant. It's a number. The temperature will be told at what temperature we are working. But what of the frequency factor? What does the frequency factor mean? Now, frequency factor is actually equal to Z times P, where in this case Z is called the collision frequency, and the P here is called the steric factor. And so collision frequency is going to tell you, remember, it is all about these 3 points we've written here. So collision frequency is the number of collisions per second occurring in a reaction. So this is collision frequency. How many collisions are there happening in a chemical reaction? So Z represents how many collisions are happening in a chemical reaction per second. Okay, that is the collision frequency. What of the steric factor? Now the steric factor is a number that is always less than 1. Okay. So the steric factor is actually a fraction of collisions with effective orientation. So the steric factor is what tells us of proper or correct orientation. This one is Z. So steric factor, fraction of collisions, or how many collisions are there which have got a correct orientation, because it's not every collision that is happening. As we can see from the first point, we've said for a chemical reaction to happen, particles have to collide. But at the same time, it's not all collisions which do what? Which give a chemical reaction happening. Why? Because some collisions are not at the correct orientation. For example, we gave hydroxide reacting with hydrogen. We said the orientation should be that this is positive, this is negative, this is partially positive. So the orientation should be this one, not the way we've put it, but it should be hydrogen this side and then hydroxide there, because hydrogen should come to the negative portion. So this is correct orientation, which we call as the steric factor. Now combining the collision frequency and the steric factor gives us the frequency factor. So we can define frequency factor as total number of collisions per second with right orientation. Because we are saying collision frequency is number of collisions occurring per second, and then steric factor is the number of collisions with right orientation. So collisions occurring per second, collisions with right orientation combined gives you the number of collisions occurring per second with the right orientation, because we are not only interested in how many collisions are happening, but we are also interested in how many are happening with the right orientation. And so combining those two gives us now the value for A, which is the steric factor. And so the Arrhenius equation can also be written in another form, that is K is equal to, where there is A we can put ZP, and then we have got E to the power negative E activation energy divided by RT. So we can also write it like that. Well, to understand it more, we are going to discuss about it in the next video. In this video, we end here.